Good morning, everyone, and welcome to the Institute of Advanced Studies water-themed lecture today. Before we have the main event, I'll just give you a little bit of context to today's lecture. The Institute of Advanced Studies was established in 2017 as part of the Calibre framework at Loughborough University, and it was really designed to enhance both emerging research areas and to foster international relationships with researchers across the globe and develop strong links with Loughborough University. Since that time, there's been a programme of activities ranging from those first events in 2017 through to 2019 and to 2021. Even though we have experienced a global pandemic, we've been able to continue a number of those activities virtually, and now we're beginning to be able to do some of them in a hybrid form where there's both people present and online. Today's presentation was part of the water theme, which was originally established in 2019, but due to events that I don't need to go into, many of those events were postponed and have been delayed. A number have already taken place, but some have been delayed, and we're picking some of them up now. And just for a little bit of context, I'm going to just go over and just remind people of the water theme as it was. The water theme was one of the programs and one of the key themes for 2019. And as part of that, there was a range of activities that we had planned and are still ongoing now, focused around a number of different themes, ranging from natural processes in the environment, rivers and water and biodiversity in the environment, extreme events, whether they're floods, typhoons or hurricanes, issues around human health and performance, and the theme which we're going to pick up today around science and technology, as well as having a cultural and biodiversity theme. So there were a range of activities, and today we're going to be focusing on the science and technology theme, and it's my pleasure to be able to introduce Professor Herman Potgieter from Witwatersrand University in South Africa. He has a number of other accolades. He did his first degree in chemistry before then doing a degree PhD in metallurgy. He has a post currently at Witwatersrand, or WITS as most people tend to refer to it, in South Africa, as well as holding an honorary post in Wuhan University in China and a post at Manchester Metropolitan University. So without further ado, I'll hand you over to our speaker today, who's going to talk around issues to do with coal fly ash in particular. So thank you very much.
Thank you, Mr. Chairman, for that kind introduction. Good morning, ladies and gentlemen, or at least it's good morning here in the UK. I know in South Africa it's already in the afternoon, so if there's anybody tuning in from there, good afternoon. I want to thank the Institute of Advanced Studies for inviting me here to talk about two things that are really very close to my heart. The one is water and the other one is waste. Now, I grew up on a farm in South Africa, and it being a very dry country, we often had droughts, so water was something, and the importance of water was something that I became aware of very early on in my life. So I hope I can share with you today some of the issues around water, which we have done, my group and I, and also to show you that waste can sometimes be very useful and used in a very beneficial way to enhance our water experience. So I am just going to share my screen. If any of you cannot hear me, please let us know now so that we can try and fix it before we start with the actual presentation. If you give me 1 minute. Okay, there we go. It seems that everything is on the screen, and we can get straight in. Sorry about that. Okay, so as you've heard, I'm from the University of the Witwatersrand, or WITS as it is generally known. And this first picture starts off with the main building at WITS. WITS University started off as a mining school just after the start of the 1900s in 1904. And in 1922, it became a university. So next year, we are celebrating our anniversary, or our centenary, rather. Sorry, I can hear you okay online. Let me hold the microphone like this. It might be better if people can hear me this way. Okay, so next year, we're celebrating our centenary, and that's going to be a very big year for us, of course. So I want to share with you today some work around coal fly ash. Now, coal fly ash is a very common material, and it's very often considered as a waste. And the reason for that is that is the combustion product of coal. In whatever process coal is used, if you combust it, there's an inorganic residue that remains behind, and we call that ash. And I'll explain in a minute to you what the fly ash part means. It simply refers to the very fine nature of this ash. So I hope that after today's talk, I've convinced you that this coal fly ash, which is being produced in millions of tons all over the world, everywhere where coal is being used in a combustion process, is really a valuable resource and not just a nuisance lying around and contaminating the world and the land area on which it is being stored or where it is being put away. So my talk today will center a little bit around how the fly ash is being produced all over the world so that you can get an indication of the usage thereof. There's roughly about 600 million tons a year being produced annually. All over the world. So it's quite a lot of rubbish, if you want to call it that, or quite a lot of very useful material that lies around. So I'll show you something of that. Then I'll give you a few scary facts about water, which really highlights the fact that we need to do something about the water in addition to doing something about our climate, because that is where our future lies. I will then share with you some of the typical applications of coal fly ash or areas where it can be used. And I will also then go into some of the water treatment work specifically that I have been involved in. Then finally, I'll wrap up with a few other applications of the coal fly ash, but the main emphasis will be on water. And then I'll give you an opportunity to ask some questions that I hope I'll be able to answer. So if we look at the fly ash production and utilization all over the world, we see a very interesting picture emerging. First of all, we notice that in Europe and the developed world, there's more utilization of this material than there is actually being produced. And that ties in with the fact that most of these countries have already started to reduce their reliance on coal. But have a look at the picture in terms of India and China, and you will very quickly see that the countries very heavily reliant on coal for their energy needs and other uses still have much more fly ash being produced than what they really utilize. In the United States, the usage and production is almost equal. And then if you look right at the end of your screen, on the right-hand side, you will see the situation in South Africa. In South Africa, we produce around about 33 million tons of coal fly ash per year. That is from coal power stations that provides electricity, and of course also from the huge petrochemical complex in South Africa in the province called Mpumalanga, where we produce fuels from coal. And the final product that remains behind afterwards is coal fly ash. And you will see that we also produce a lot more than what is currently being used. Now, the moment that you go onto the internet and you type in coal fly ash, you will find that there are quite a few books and literally thousands of papers that deals with this particular material called fly ash and areas where it can be used and where it is useful and what it can be used for. So I'll just highlight a few for you that I've been involved in over the years. I've looked mainly at water treatment. Then I also did some work associated with beneficiated products. And then I think the final area that one can identify where this is becoming increasingly important is metals and minerals valorization. With the emphasis nowadays on circularity in the economy, it's very easy to say, well, so what? Are these applications green? And I hope I will show you that a few of them actually help to enhance the circularity of the use of coal into other products or into useful applications. So if we start off with the water treatment part, we have done some work in my group on the removal of potentially toxic elements from water. Those are mostly heavy metals, if one wants to give it another name. Then I'll show you how useful this can be to also remove fluoride from water. Now, it's not everywhere in the world, but there are quite a few areas in the world where fluoride in drinking water or groundwater resources is a problem. And as you may probably be aware, too much fluoride gives you an illness called fluorosis, which eventually leads to the embrittlements of your teeth and your bones. So quite an issue in some parts of the world. Acid mine drainage is a treatment where we've applied fly ash in my group. Now, wherever you have old coal mines or old gold mines, where pyrite is part of the mineralogy and the minerals that occur in the mine, we find that that pyrite can then be oxidized the moment it's exposed to the atmosphere, and it then starts to oxidize and produce a very, very acidic effluent. And I hope I'll show you a little bit later in this presentation what this looks like. It really is a horrible effluent to treat. And in all areas where you have old and as well as current coal mines or gold mines, one finds that this is a problem. In the UK, I believe some of the mines down in the Cornwall area where tin and copper were originally mined also have this problem of an acid mine drainage that seeps from the mines, and that requires treatment because it contaminates the environment. We've used fly ash for phosphate removal. That is another well-known contaminant in water treatment, as you are probably aware. When you have too much phosphate in the water, it encourages algae growth, and that then leads to oxygen starvation for the aquatic organisms in that water body. So ideally, you do not want to have too much phosphates in your water. Also, phosphate is a limited resource. It's used in fertilizer. So ideally, one would actually like to recover the phosphate and not just remove it. We found remarkable success in treating bacteria with slightly modified coal fly ash in the form of zeolites. And then we also had a bit of success with some of the persistent organic pollutants, which one typically finds in water bodies. And those would typically be the humic and fulvic acids that originate from plant growth on the banks of a canal or a river. There are some phenols, which is typical from the effluents of steel factories, of petroleum plants, even some pharmaceutical industries have phenols in their effluents, and then a legacy from the textile industry, which is the group we call dyes. Now, of course, there are different types of dyes, and I'll just show you later on how one can apply the coal fly ash to treat an effluent containing dye and what the nature of the dye is in terms of the influence on the process. Okay, so again, the green applications are probably with the first sight, acid mine drainage. And I guess for the rest, it depends very much on your perspective and whether it is a problem in your part of the world, whether you consider this to be a green application of coal fly ash or not. Some of the beneficiated products we looked at include refractory products. You may be aware that all the high temperature processes like glass making, steel production, cement making require refractory linings in the reactors or the furnaces, and one needs to be able to protect your vessel in which the reaction occurs or in which you make your product. And I'll show you why the coal fly ash is particularly suitable for that type of application. We also made ceramic filters, which we used in water treatment to filter water. And you can imagine that being a kind of sponge material or looking like a sponge that you would use in your shower. And we made ceramic filters with that. South Africa, being a mining country, has a lot of old mines where we don't do any mining anymore. And you have to make sure that you do some backfill in those worked out areas. Otherwise, you have problems with subsidence on the surface of your mine or the surrounding area. So in mine backfill operations, coal fly ash is a very useful component. Then you can make something called geopolymers with it. Geopolymer is an inorganic type of polymer consisting of various silica tetrahedra connected together or silica alumina units in the polymer, very suitable for immobilizing heavy metals, especially if they are radioactive. And there's been quite a lot of work done in that area. Zeolites is something else that one can manufacture from coal fly ash. Zeolites, very well known for applications in terms of catalysts, also in terms of water treatment, and I'll say something about that later on. Then I'll show you from the nature of coal fly ash why it is very useful in polymers. As you may or may not be aware, polymers contain a fairly large proportion of inert fillers to make up the material. The material most often used for that is calcium carbonate or limestone, but the coal fly ash offers certain advantageous properties which you don't necessarily get with calcium carbonate. Then something else we looked at is thermal barrier coatings. We haven't done much in that area. We've tried various coating technologies, things like high velocity oxygen flames and spray coatings and whatever. Didn't have much success with it because we find that you actually need a type of a glue that can hold the fly ash onto your substrate that you're coating with it. And when I show you the nature of the coal fly ash, you will understand why it falls off. The area where coal fly ash is mostly used is in the building industry as a cement or concrete addition. Now in cement, you can replace part of your cement with the coal fly ash, which gives very advantageous properties to your cement. The moment that cement reacts with water to harden, it is an exothermic reaction and it produces calcium hydroxide as one of the products. Now that calcium hydroxide can react with a coal fly ash and it can then enhance the cementitious type bonds that form within the material. On the other hand, the dilution with coal fly ash also means that you do not have to worry about thermal cracking afterwards because of this exothermic reaction in your material, because the delayed reaction of cold fly ash compared to pure cement reduces that amount of heat which is being released. So in concrete, it is very advantageous. It reduces the thermal cracking, as I've said, and then also it enhances the fluidity of concrete mixtures. Now, when you have to pump a concrete mixture, you would ideally like to have some cold fly ash in there to increase the pumpability and to facilitate the pumping of the concrete. So again, in terms of green applications, geopolymers is the one that stands out, but probably some of these others qualify as well. Now, the latest area where coal fly ash is receiving a lot of attention is in the recovery of metals from it. So the metals and minerals valorization is a fairly important, currently developing area. It started off by some work that was done at the University of Kentucky to have a look at the amount of rare earth elements that occur in fly ash. And because it is such an extremely potent process to concentrate metals within a solid matrix during the combustion process, you find that even although there are very small amounts of metals in the fly ash, due to the volume of fly ash that one deals with, it is actually quite a sizable tonnage that you have. And as you may be aware, rare earth elements nowadays are an extremely important part of our green economy for all the new technologies in terms of energy storage, renewable energy recovery, and similar types of applications. Alumina recovery is something else that a number of people have looked at over the years. There are various processes, either acid-based or alkali-based, that allows you to recover alumina from fly ash. I think at this point in time, the price of the acids and the alkalis being used in the process makes it slightly too expensive to compare with bauxite that you dig out of the earth. I know that in South Africa, it is cheaper to import bauxite from Australia all the way across the ocean, offload it in a harbor, and then recover alumina from that. You may or may not believe this, but silica or sand for building applications is another area where there's a scarcity of suitable sand, because when you put sand into concrete, it needs to have a certain particle size distribution, certain form, and excuse me, it is not just a case of driving to the beach and picking up a load of sand to add to your concrete. So silica recovery is another area that one can potentially look at. And I think all three of these areas are helping with the circularity of the economy, using a waste product for something useful that we can apply in other areas. Now, what on earth is this coal fly ash and what does it look like? And it doesn't matter whether your fly ash originates from coal combustion, from biomaterial combustion, from municipal solid waste combustion. This is the form that it typically has. It is these little spherical particles which are hollow inside. Now, the fact that they're hollow will immediately indicate to you that in areas where you need insulation from heat, sound, or something like that, they could potentially be very useful. Hence their application in refractory products because of their heat insulation properties in the material or in the composite that you manufacture containing them. You will also see that there's quite a large size distribution of these fly ash particles. They typically range from about 5 micron up to about 110 micron. And with a process called classification, one can easily classify them or separate them into various size fractions if you so desire. Excuse me about that. So, you will also notice that due to their appearance, they resemble ball bearings. So you will understand that in areas where flow or rheology is an issue, these little particles, or small ball bearings, liken them to something again, may be very useful to use. So let's move on to the area then that I really want to talk about, and that is the wastewater treatment. You may be familiar with this quote from a British poet, which says that thousands of people can live without love, but not one without water. And we know that from our own experience. So let me give you a few scary facts about water. Projected water stresses in the world by the year 2030. And ladies and gentlemen, this is a mere 10 years away. Looks something like this. You will notice that the desert areas of the world are covered in gray. So they are already severely water stressed. What is interesting is the areas adjacent to them in the dark red, dark orange colors that are due to become water stressed. Though one associates Europe with a fairly wet part of the globe, it is actually projected that by 2030, the picture might change dramatically. You will also notice that in North America, where most of the United States and Mexico is, there are future troubles ahead in terms of water scarcity and high water stressed areas developing. And this, of course, all has to do with climate change, which we have just seen in the COP conference, which occurred in Glasgow a week or two ago, is on our doorstep, and we have to do something about it. If you look at the south point of Africa, where South Africa is situated, you will see that it is already a very water-stressed region of the world. It is actually only the eastern side of the country where there's a reasonable amount of water. The rest of the country is notoriously dry, suffers from frequent droughts. And you might have seen some horrible pictures about that recently on television, areas where there hasn't been a drop of rain for 7 years. So water scarcity is on our doorstep, and it is going to become worse. What is even more scary is that 80% of our current wastewater in the world flows back into the environment without being either reused or retreated. And these are figures that comes from the United Nations. Just over 10% of people on this planet lack even basic drinking water, while 144 million of them are dependent on surface water. And I'm sure you've also seen the pictures on television when non-governmental organizations and charity organizations ask for donations to put up water treatment facilities in developing countries. Even more scary, and I hope this is not the case in most places that you are familiar with, where there are frequent reports of sewage and effluents being released into rivers. 2 billion people on this planet already drink contaminated water. Not a very nice thought to deal with. And then something else, which is really on our doorstep. It is a mere 4 years away, and it is projected that half of the world's population will be living in water-stressed areas. Now, if this doesn't scare you into some action, I don't know what will. So let's see if there's something we can do about this, and if there are some materials we can use to help us to address some of these problems that that we're facing. Now, of course, every solid surface has the capacity to absorb solutes onto them. So why is coal fly ash so suitable there? Well, as you've seen from the picture that I've shown you when I showed you what it looks like, you can imagine that it has a fairly large surface area. So, of course, it has a lot of areas where there can be potentially adsorbents taking place. The other material, which is quite often used, sometimes in conjunction with coal fly ash, sometimes on its own, are the group of materials that we call clays. So if we look at the adsorbents and we divide them into the two types of classes which occur as either naturally occurring materials or materials originating from manufacturing processes, we see that between the clays and the coal fly ash, we have quite a few opportunities and potential uses that we can apply in the area of water treatment. So just to start us off, I'll show you a little bit about some of the work we've done with clay, just as a comparison for some of the stuff I'm going to deal with later on. You will see that in South Africa, here in the northern part, around the areas of Naboomspruit, Warmbad, Malboom, we have a particular type of clay deposit, which is called palygorskite. Now, the palygorskite has a 2-1 layered structure and is very suitable for water treatment because there are lots of spaces where adsorption can take place, where some of the current water molecules or metallic cations can be replaced by others. So it is a very suitable material for that. I'll also show you later on that in terms of fluoride removal, the coal fly ash is very useful. And again, it comes back to this northwestern part of South Africa where there's quite a lot of fluoride contamination in the drinking water. So although you can fairly easily warn human beings not to use that water, what do you do with livestock if you are a farmer in that part of the world? So what we've done is that we have started off by looking at some typical metal ions that occur in water effluents, especially in industrialized parts of the world, in certain processes, chrome, especially from chrome plating plants. And we have investigated the adsorption thereof in terms of the clay, because very often coal fly ash is used for this adsorption. So one of the things that we have found is that we could describe the mechanism of the process very well with two well-known adsorption isotherms, the Langmuir and Freundlich isotherms. And the other important part of the information that we need in terms of designing a plant eventually is, of course, the kinetic results, so that we can do our reactor design. I'll show you a little bit later how we've compared certain process options for water treatment in terms of the costs and the kinetics involved. So we found in this case that we were dealing with a first order equation. Now, in terms of the coal fly ash, sometimes it agrees with the clays, and sometimes they actually obey a different kind of kinetic model where we're dealing with second order kinetics. And interestingly enough, something that I've noticed over the past 30 years that I've been working with this material is that it doesn't matter which heavy metal atoms or heavy metal removals you are investigating from water and with what type of material it is. The lead always seems to adsorb extremely well. better than anything else. The reason for that still escapes me. I think it will possibly be a good idea to investigate that very fundamentally one of these days. You will also notice that as the concentrations of the heavy metals in the water increases, the efficiency of removal obviously decreases, and that's not strange. That is, as the number of adsorption sites get saturated, there are less and less sites available to absorb the heavy metals and remove it. So, some of the other work that we've done involves the removal of phosphates and fluoride, as I've already said. We've looked at some iron and manganese removal from water. And whenever you deal with water that has a high organic carbon loading in it, your normal treatment processes become less efficient. And you need to start making some adjustments. We've also compared that with one of the methods often used for this type of water, namely nanofiltration. Then we looked at some phenols and dyes that we can remove from water. We looked at using the fly ash in terms of acid mine drainage and how that compares with the standard types of materials like limestone and dolomite, which is usually being used for acid mine drainage treatment. And as I've said, we also considered some antibacterial applications. So I'll just briefly take you through some of these and show you some of the things that we found. Now, both fly ash and blast furnace slag are industrial byproducts. Both of them contain calcium oxide. The slag, the blast furnace slag, contains a larger proportion of that than the fly ash, and that explains why we see in this picture that the slag is more effective than the fly ash, which is the top curve, to remove phosphates from water. That can, of course, be ascribed to the fact that calcium and phosphate forms an insoluble or a sparely soluble compound called calcium phosphate. Again, we have found that if we look at the mechanism of the adsorptions, that we can get some clues from the adsorption isotherms. Contrary to the clays, the Langmuir and the Freundlich adsorption isotherms, which describes the nature of the adsorption process, provided very poor fits for both the phosphate removal with slag and fly ash. However, if we used another approach, the Frumkin adsorption isotherm, we see a very interesting thing. We notice that these alpha constants in the Frumkin isotherm have much higher than usual values. And that gives us an indication that there must be an interaction between the adsorbed molecule and the substrate. And as I say, it is not strange because both these two compounds contain a little bit of calcium oxide, and the formation of the calcium phosphate would naturally result in the higher values that we see in the Frumkin isotherm. If you have fluoride problems from your process, the standard way of treating it to get rid of it is using one of two types of compounds, either titanium dioxide or you use alumina, and especially activated alumina after it has been treated with a little bit of sulfuric acid. Now, what we've done in this particular investigation, we said, okay, let's skip the typical applications where we have fluoride in the drinking water and it seldom goes above 10 milligrams per liter. By the way, the safe level is 0.7 milligrams per liter of fluoride. So if you look at your toothpaste next time you brush your teeth, you will see that it's actually above this level. And that is because you need an excess of fluoride to react with the enamel in your teeth to strengthen it. But we looked at the industrial effluent with something like 500 milligrams per liter of fluoride in the wastewater. And we thought, let's take the standard approach of using titanium dioxide and compare it with what we can get with the coal fly ash. And you will notice that, especially as the dosage of the coal fly ash increases, that the performance is very similar to that of the titanium dioxide. In both cases, we can remove about 20% or more of the fluoride in that highly contaminated wastewater. So an area where I think there's much scope for the coal fly ash to be applied in future. If we look at the absorption capacity of the two materials, we see that it's vastly different. The titanium dioxide is at least a factor of 100 to 1,000 more than what the fly ash is. But because of the, apologies for that, because of the difference in their cost, there isn't much difference in the ultimate treatment costs. Very similar, about 10 times more expensive with fly ash, but then on the other hand, you're using a material that is just lying around. You don't have to go and dig it out of the ground, beneficiated, and cause a lot more carbon dioxide emissions along the way before you actually have titanium dioxide. Okay, when we looked at phenols, this is a particularly difficult effluent to treat, and we considered two derivatives of phenol, 2-nitrophenol and 4-nitrophenol. Now, if you recall from your chemistry days, phenol is a benzene ring with a OH group on the one position of the 6 carbons forming the benzene ring. Now, the 2-nitrophenol is the ortho substituent of nitro, of a nitro group, a nitrogen group, NO2, and 4-nitrophenol is the para substituent. And we see an interesting observation here, and that is where the removal of the phenol and the nitrophenol are very similar. We find that when we deal with the 4-nitrophenol, it is a lot better. And the reason for that can be found in the chemistry of the molecule. The nitro group is an electron withdrawing group, so it weakens the bond between the oxygen and the hydrogen of the phenol group, makes the hydrogen a lot more mobile, and it then leads to the phenol acquiring charge, and the charged species then absorbs very well onto the fly ash. Now, initially, the student that worked on this, who's now Professor Bada at Wits University, tried to monitor this reaction with gas chromatography, and in the end, we found that actually simple UV vis spectrometry was very suitable for the work and monitoring what was going on. In terms of the adsorption isotherms that told us a little bit about the mechanism of the reaction, we found that the Langmuir adsorption isotherm fitted reasonably well, which indicated a type of single molecular layer adsorption onto the substrate, which in this case is the fly ash. We found that we could remove 3/4 of the phenols, regardless of which specific isomer we were looking at, from our effluent. And as one would expect, pH played quite an important role in this process. What we also then tried to do was to recover the phenol or the nitrophenol from the coal ash onto which it was absorbed. And we really struggled with the 4-nitrophenol. It was much more difficult to remove that compared to the phenol or the 2-nitrophenol. And we think that it had something to do clearly with that bond formation that took place because the molecule acquired a negative charge in the process. Okay, if we look at dyes, which is the other well-known area where coal fly ash can be used to remove organic type materials from wastewaters, we've investigated two types of dyes. The one is methylene blue as a model compound for the cationic type dyes, and the other one was methyl orange, which is a model compound for the anionic type of dyes. And I want to show you how the chemical nature of that dye plays a role in this whole process. There are two things we should observe here. The one is, if you look at this middle column of the absorption, maximum absorption, apologies for that, the values of the maximum absorption, we see that it hovers around 6.1 milligrams of the dye being absorbed on every gram of the adsorbent, which in this case is the coal fly ash. So that's the one area that we need to keep an eye on. The other one is the activation energy of this process. And you will see that it has a fairly high value for an adsorption process. Now, this indicates to us that what we were dealing with in this case was chemisorption. In other words, this is a partial or a full chemical bond that develops between the molecule that adsorbs onto the coal fly ash and the coal fly ash itself. We also noticed that, again, if we compare different process options for the treatment, say a batch process versus a column process, that the mechanism describing the adsorption in each particular process differs. In the column, it was mostly the Langmuir adsorption isotherm that describes the mechanism of the process, whereas with the batch process, we found that the Freundlich isotherm described the mechanism of the process much better. Apologies for that. Then we did a comparison between the different options of treating the effluent. And you see here three options. Now, the column is a very well-known unit operation to treat wastewater in. Whether you use activated carbon or any other type of adsorbent, clay, coal fly ash. And when we started to crunch a bit of the numbers in terms of the costs, which is indicated on the right-hand side in red, you can see that the column process clearly comes out as the most economical one. It also requires less fly ash than the other two processes. Notice the difference between the batch process and the heap process. Now, in heap leaching, what one typically does is you have a heap and you try to leach your metal of interest from the heap with some or other type of solution. In this case, we use the heap leaching approach, and we use the heap to see if that doesn't give us a simple and cheap way of removing the methylene blue from the effluent. And we found that, not surprisingly, or well, in line with the fact that the column process is very popular in water treatment, that it actually reduces the best results at the cheapest possible price. Now, if we move on to a different type of dye, which is the methyl orange characteristic or the model compound for anionic types of dyes, you will immediately see some differences between that and the cationic type of dye adsorption onto the coal fly ash. If you look at the last column in this table, you will notice that the maximum adsorption capacity of exactly the same material, coal fly ash, that we've used, is now 10 times less. It's a factor of 10 less than it was with the cationic dye. The other interesting thing is the activation energy of this process. It's about a third of what it was for the cationic dye. So that immediately tells us that the process going on here is very different from what we have with cationic dyes. And that is something you need to take into account in design of treatment systems, depending on the type of dye or textile effluent that you're dealing with. This lower value of the activation energy indicates that it's unlikely that there's a chemical type of bond or partial chemical bond that occurs here. This is purely a physical chemistry, physical adsorption process onto the material that you use for the adsorption. We also notice that as the adsorbent dosage, the coal fly ash dosage increased, there is more of a similarity in the amount of dye removed between a batch process and a column process. The green and the blue represents the two different processes. If we use a small amount of dosage, the column process clearly is almost twice as efficient as the batch process. However, as the amount of coal fly ash that we use increases, the efficiency became very much the same. Okay, and again, we did a few calculations, very sort of back of the envelope calculations about costs. And once again, the column process is the cheapest for the removal of the dye if we have to pick between different process options or unit processes to do the removal with. So finally, if we look at some of the acid mine drainage, you will see that this is a horrible effluent to deal with. Your pH is about 1.2. You have large amounts of iron in both the +2 as well as the +3 state in your effluent. The sulfates are sky high, more than 6,000 parts per million. And as we know, calcium alone is not efficient in removing that amount of sulfates as gypsum from, or as calcium sulfate from the process. So what we investigated was how pH played a role in this, what the role of contact time was, the particle sizes of the materials that we used, and what residual amounts remained afterwards. And I'm just going to quickly show you some of the results. You can see that as the dolomite dosage decreased from 160 here on the left-hand side, right at the top, to about 40, the contact time that we need to neutralize this effluent increases dramatically. Not so much with the limestone, a lot less dramatic effect. And for the fly ash, we only used one particular dosage, now only 500 milligrams per liter. That's why the left-hand side y-axis has a different scale than, or the right-hand one from the left-hand one. Okay, so in terms of the correlation that some of our other colleagues found, there's a group at another university in South Africa that have also done something similar, and they have found that with the 500 grams per liter of the fly ash, their pH actually increased to 7 instead of 5.5. And they could achieve this in 150 minutes, whereas we took 4 hours. Now, that is important because it indicates that the nature of the fly ash that you use is important. And that nature, to some extent, gets determined by the combustion process from which one derives this fly ash. This just shows the effect of pH in the process, how it changes over time with different amounts of fly ash being used. And not surprisingly, as the amount increases of whatever reagent you use, whether fly ash, dolomite, or limestone, the ultimate pH that you reach and the ultimate amount of removal of the iron increases after a period where it seems that there is a plateau in the process being reached. If one looks at 30%, that 30% removal can be achieved at pH slightly above 4. We know that for iron type of compounds and their precipitate formation, pH is quite important. If we go to a slightly higher pH, we notice that that removal decreases now to 10 to 15%, except if you go for a very long period of time. Okay, so in terms of the sulfate removal, not much of a difference between the, excuse me, the 4 hours contact time treatment and the 6 hours. You'll see that the amounts are very similar. The final amount for the fly ash is exactly the same. However, if your treatment time is too short, you hardly remove anything. So it seems that there's a point where you have at least a minimum amount of a certain reagent needed for the successful removal of sulfate, and that it is also dependent on how long the contact time is. Now, these are all, of course, important considerations when one gets to designing a process for it. I think this shows exactly the same thing. Right, so let's look at some financial implications. And we see that despite the fact that we use almost 10 times as much fly ash as limestone, that the final pH that we can achieve is very similar to the limestone treatment, and we can do it at almost half the price. If we look at the 100 milligrams per liter of limestone compared to the 500 milligrams or the 500 grams per liter of fly ash, sorry, it's 100 grams per liter, and the 500 grams per liter of fly ash, that we sit with half the cost in terms of the fly ash treatment than the limestone. Okay, so the last one I want to show you before I sign off is this one in terms of the bacterial treatment. Here we've used the coal fly ash to make the zeolites, and we loaded the zeolites with silver particles or silver ions and copper ions. And we then looked at the efficiency of killing of bacteria in water, because apart from your organic and inorganic contaminants in water, bacteria is, of course, the other big issue that one needs to worry about. We found that especially the zeolites containing silver were very effective. They could kill both gram-positive as well as gram-negative microorganisms. The FAZ4 and FAZ10 indicates the amount of loading of the silver onto the zeolite. And you can see that as the loading increased, the killing of the bacteria was a lot more efficient. It was also a lot faster. The copper, to our surprise, didn't work as well. It worked for the Escherichia coli, but for the Pseudomonas aeruginosa and the Enterichia Fecalis, it was totally ineffective. Okay, so I just want to show you some other applications that we've done over the years. In one particular instance, we used a problematic waste from a ferrovanadium plant, and we immobilized it by treating it at a temperature of around 600 degrees with coal fly ash, and we formed an aggregate that you can use together with concrete in building applications. We looked at surface properties of the fly ash, and that work later on became very useful when we looked at the effect of coupling agents and the interaction of coupling agents between the coal fly ash and polymer matrices for some of the composite materials that we made. And the reason for that is that you can imagine that polymer being an organic type of material, coal ash being an inorganic type of material, that the two don't sit very well together, except if you have something that enhances the bond between them. And the type of compounds usually used in the polymer industry for that are called coupling agents. And the coupling agents are also used to prevent certain degradation. And that's one area where the fly ash composites really help. If you make a composite containing fly ash, your degradation is a lot slower than if you don't have fly ash and you use other types of fillers in your material. So all this worked nicely, dovetailed in the end, and helped us to produce a few interesting MSCs from it mostly. If I'm not mistaken, one of the external examiners for one of these MSCs was actually a member from Loughborough University. I'll go and check my notes. This was a few years ago. So finally, one of course has to say thank you to all the people that have helped to produce all these results. I'm just sitting here telling you what they are and showing you all these nice pictures. Some of my colleagues at Pretoria Portland Cement in the days when I was still in private industry contributed, of course. Then some of my students at the Technikon of Pretoria, which are nowadays the Tshwane University of Technology, did some of the work. Some of the students at WITS, at Manchester Metropolitan University, we did most of the polymer work with colleagues there and some exchange students from Spain. The National Research Foundation provided some funding during the course of all these studies over the last 30 years. And then two companies, Ash Resources in South Africa and Rocktron here in the UK, provide some of the materials that we used. And then I want to thank Loughborough University and in particular the Institute and my hosts at the Department of Chemical Engineering, Dr. Das and Dr. Lieper, for inviting me here and hosting me. I really appreciate that, and I hope I have convinced you of two things. The one is that water is extremely important. So next time that you stand under a shower or you open a tap, give some consideration to what a valuable resource and necessary resource water is in our lives. And the second thing is never throw anything away. Even waste can be very useful sometimes for the treatment of problematic environmental problems. Now, if you have some questions, I'll try and answer if I can. Thank you very much for your attention and giving me this opportunity to share some of our work over the last 3 decades with you.